In this video, I'm going to go over practice questions for grade 12 general term 1 physics exam. So this is starting off with the first topic, interference and diffraction. So I have made a video on interference already and solved all of the multiple choice problems, but I will go over the focused ones. So, as mentioned in my other video, light sources are coherent if they have the same frequency, same wavelength, same phase. Coherent just means that they are going together, like that, in a smooth operation, smoothly going along together, no changes being made. That is what we call coherent. Next, when waves interfere constructively, what happens to amplitude? So constructively, if just to remember, that means the crest and the crest will meet and join together to create a bigger wave. The trough and the trough will meet. They are in phase. They are in perfect phase together. So that means if it's constructive, it will increase. However, if it doesn't say constructively, if it said the other word, destructively, then it would be the opposite. You would see something like this, meeting with the opposite. Now you will see the crest and the trough and the crest, plus minus. They will cancel each other out. Then you would pick decreasing. And it would only become zero if they are perfectly out of phase, exactly opposite each other. Then you could say it becomes zero, because this does cancel. If this was plus 1 meter and this was minus 1 meter, that will become zero, of course. So it would depend on the question, of course. Next, destructive interference, and I've already answered this, is when a crest meets a trough. You could have said maxima meeting a minima. Maximum is the same as crest. Minimum would be the same as trough. Max is the top, minimum is the bottom. So of course, B is the answer here. Very nice. Let's move on. Which fringe is the third order maximum? That's all they're asking for this question. No need to use anything else. So if we have the center over here, this is the center. We're talking about not 1, 2, 3 along each side. 1, 2, 3. The third order is E. That means clearly the second order must be D. This is number 2. This is number 3. You could say the first order is C, or you could say A. Both are 1 away from the center. So you just count from the center. The brightest one, you count from here. 1, 2, 3. That's how you'll get the answer, E. And over here, we now need to see what happens to the slit spacing what happens to the spacing between the fringes if I make some other changes. So first things first, we need to know that this is still talking about the same formula, which is the one from before. We have the rule lambda equals xd over L. This is how it's given to you in the formula sheet. Lambda equals xd over L. And have they arranged it? No, so you have to figure it out from the formula sheet. They're asking you for x in this case. So that's easy to rearrange, to be honest. If you start with this formula, you can get to this. You can memorize this if you like, or you can just rearrange. Use a bit of algebra. I want to make x the subject, so I'm just going to keep it here. I'll remove everything else. To cancel the L, it is dividing right now, so using grade 9 maths, I can figure this out. Multiply both sides by L. If I do that, I cancel. This becomes lambda multiplied by L equals x, and I have the D here, and it's multiplying. To cancel the D, I will divide both sides by D. I will divide both sides. That will cancel the D. Long story short, I now have lambda L over D. That equals to x. So I've got it right here. If the slit separation is increased, what happens? So now you can see that the x, which is the fringes, x is for the fringes. Again, if you forget, it is written here. X is for the fringes. It's written there. In case you don't remember what each one means, it's all here. So let's find out. It is directly proportional with everything above the line. It is inversely proportional with everything below the line. What does that mean? Well, if I increase my wavelength or my length, the distance from the screen, this will increase. If I increase this, then this one will have to decrease because I'm dividing by this. I'm making the fraction bigger. 1 divided by 2, 1 divided by 4, 1 divided by 8. The number gets smaller, becomes a fraction. Okay, so if the slit separation will decrease, no, it says here increase, that means this fringe spacing must decrease. These two are opposite each other. So that's what you can say. Next, color switch from red to blue. So for this, you need to remember the order of the colors to help you get this. And there's a little trick just called Roy G. Biv. Roy G. Biv. B-I-V. Red, orange, yellow, green, blue, indigo, violet. Many people forget what that is. That's just purple. So like there, purple. Okay, so what am I doing? Yes, this is a high wavelength and this is a low wavelength. So if I switch from red to blue, I am going from red that way to blue over here. My wavelength is decreasing. Back to my little relationship, which I've written here as well. But my relationship, if I decrease this, it is directly proportional to my x. It will also decrease. So that will decrease. And it makes sense because the waves are shorter, so the fringes will be narrower. They'll be closer together. Makes sense. Monochromatic light is replaced with while light. That should be a T, white light. If that is happening, well, it's asking me what happens to the fringe spacing. So if I replace it with white light, it won't make an effect on this fringe spacing, but instead you will see a big white band in the middle, and you will see colored fringes, like the rainbow on the sides. So they've mentioned what would happen, but you didn't really need to write this. They're being extra, because it asks you what would happen. Technically speaking, nothing happens to the fringe spacing. You will, however, see coloured fringes at the sides and a big white central band. We can probably write that. White light, let's check. White light diffraction. Let's check. There, right there. White and then the coloured fringes on the sides. Okay, very nice. Let's get back to where we were. Very nice. If I increase the width of the two slits, well, that is the... Well, it's not really there, is it? There's nothing here written about the width. I don't see anything. So actually, again, nothing will happen. However, they did tell you a little bit extra. If I increase the width, so if I had a narrow width like this, yeah, a little bit of light will pass through. If I had a bigger width, more light will pass through. So that simply means the brightness will increase in the center. This will have a little brightness. This will become more bright, because more light was able to pass through. So the width will not affect the actual fringes being, spacing between the fringes, but you will see brighter fringes, more intense light. Very nice. So let's move on to the next one. Over here, we're using the calculation. So if you come across this as an exam and you're going to see two slits separated, first order bright band, this much distance from the central band, and a screen, what is the wavelength? You would go to your formula sheet and you would think, what am I talking about here? Well, there's nothing to do with electrostatics. There's nothing here about wavelength. It must be over here. It must be the first lesson. We have a wavelength, so my formulas are coming from here. If I'm reading the question now, two slits. Okay, so we're talking about something about slits. We have slits written right here. I will see that this is something interesting. And then what else does it say? A band on a screen. A screen. Then we will see distance of slits from the screen. This is starting to look interesting. We have the X, we have an L, we have a D. We're going to end up using this formula here with the wavelength. Do we have a wavelength? We need the wavelength. This is how you try to figure out which formula to use. I have kind of figured out now. First order means m equals 1. That's not an L, that's 1. And that's basically over here. That's xt over L. This is the same thing. M lambda is xd over L. This becomes 1. It doesn't change anything. So long story short, we have our formula. Is this one or this one? You just replace that with the number 1. M equals 1. The order of the fringe, which is clearly 1. This must be my X. It's saying the first bright band appears away from the central band. So if you were to just try to think of it as a picture, just to make sure we're okay with this, you will have the light passing through. This is going to be the D, the distance between the bands, not the bands, the distance between the slits. This will be my L, the length of the screen, and each of these are going to be my X, the small ones over here. Okay, so the reason I went more detail in that is because you can kind of figure out the formula numbers and answer yourself. You've got the XD and the L, you just put the numbers in and you can get the answer. Just need to remember, that's millimeters. Milli is times 10 to the minus 3. By the way, milli you need to know, micro you need to know, nano you need to know, maybe even centi, both you need to know. Centi is easy, it's just divide by 100, which is the same as times 10 to the minus 2. This is times 10 to the minus 3, and then this is micro, which is like a little u, that's times 10 to the minus 6, and finally nano is times 10 to the minus 9, and that's easy, nano 9, nn, nano 9. Right, which one is showing the best waves, the wave fronts? Well, the only one that makes sense is when the light bends. This is what this does, this is diffraction, this is when light bends through a gap. And I've just mentioned it now, when it passes through a narrow gap, what is it called? It is called diffraction. Refraction is when a light changes direction, something like that. Polarization, well, there's two types of polarization. You get polarization of charges when you have plus on one side, negative on one side, or you have polarization with light where it blocks some of the light, like polarized shades, the sunglasses that you can get, and they are sometimes polarized, like the Ray-Bans, they have a little P on them. That's my attempt at drawing shades. Anyway, interference is when two waves meet. So that's the meaning of each of these. This asked for diffraction. Alright, let's move on. What type of pattern is produced by a single slit of coherent light? Single slit, you will get a wide band in the center and then some small bands on the side. Actually, it's done here better in this little diagram. Let's look at this. Single slit is one, you can remember one slit, one big band. That's an easy way to remember it. Single slit, one big band, and you'll get something on either side. Then if you have a double slit, you get a little bit more. And then if you have a diffraction grating, you get a lot more. The idea here is, I've got it over here. If you look at this, I hope we can see. Yeah, so in this one slit, scientists noticed that, okay, there's something going on over here. What would happen if I added another slit? And then they've seen a lot more of this interference. So they say, okay, let's add more and more and more and more. And as they kept adding more, these little lines got sharper and sharper and clearer. By the seventh slit, it's getting much clearer. It's easier to see and feel the difference between each of these dots. You can measure the distances, you can even calculate wavelengths from this. This is helping us figure out the wavelengths of light and things, just by measuring these distances and all of that. Now, if you move on to the diffraction grating, that is not just 7 slits or 8 slits, it's thousands of slits, tens of thousands, hundreds of thousands of slits, so much so that you will get a perfect, nice little beam. And I think you will see it on the next slide. Yes, it's here. Look at that. They are very, very clear, very accurate, very easy to see. Single slit, you have a nice bright band, and then it tails off. Double slit is nice, equally, equal brightness kind of, but then just it's really wide, each of them. So it's not as easy to pinpoint where you would measure from. You would do that from the diffraction grating. Anyway, let's move on. Now we're trying to figure out something about the width of the central bright band. So we have light of a wavelength and we have a width. Let's check our formula sheet. Width, where are we? So it says width over here, width of a central band. What is the width of the central band? You can easily figure out that this is the formula. You'll get 2 marks just for identifying the formula. You will just write the formula, 2x equals 2 lambda L over W. Now one thing to point, this 2x is a term. It is not 2x, the same way that this is 2 lambda. The reason why is that this is a bright band. If you remember the bright band, let's go back to this over here. This is x over here. However, this is 2x. There is another x from here to here, that is x. We have another x and x, 2x. That's where this 2x comes from. It is a term. This 2x simply means the width of the band, the total width. You will be given the distance x over here, or in this case, you have to find the total width. If I asked you for the x, you can then divide by 2. But 9 times out of 10, you will be asked for the width of the central band, in grade 12 general at least. Okay, direct substitution, no need to rearrange the formula or do shift solve. 2 lambda L over W. 2 lambda, that's the wavelength. Remember, this is nano, 410 times 10 to the minus 9. I mentioned it is important, it will be coming a lot. Then you will do multiplied by L. It's not written here, but you see it in the question, 0.29. So 2 lambda L divided by the width of the slit, minus 6. They could have written micro, but they didn't. So 3.8 times 10 to the minus 6. You'll get your answer, done. Answer should be in meters. That's another point I want to make here. All of these are meters. If you have no idea what unit to write, just write meters for default. If you don't know anything, just write M. You will get 1 mark for writing this. You have a chance of just getting a mark for writing the unit. And you can't get it wrong. They're all units of meters. The only thing different is this little angle. We all know, hopefully, angle is in degrees. So that's another little tip there for you, especially for topic 1. Next, we have a diffraction grating, 6,000 lines per centimeter. And we have everything in centimeters, so I don't need to convert this to meters at all. If you see this number of lines and you want to see the distance between the lines, that's the same thing as the distance between the slits. There is the D, distance between the slits. All I will do is take my 1 grating and I'll divide that by 6,000 lines per this centimeter, and you will get, well, if you put it in your calculator, this number here, 0.00017. That's the distance between each narrow slit in this diffraction grating. Told you they're big numbers. Okay, next we have monochromatic light from a laser. Wavelength is here. It is going on a diffraction grating here. Find the angle. Well, that's easy now. We only have 1 formula with an angle. Out of everything, there is my formula. So you can identify the formula straight away, get yourself 2 marks just like that. D sine theta equals m lambda. What you could do is rearrange the formula, or you can do shift solve. Just make sure your calculator is in degrees. If I wanted to just write the numbers in, you have them over here. D, which is here, 2 times 10 to the minus 3 millimeters, right? 2 times 10 to the minus 3, minus 3. Minus 3 minus 3 is just minus 6. So that just becomes, I'll write it again, 2 times 10 to the minus 6. Minus 3 milli, which is also minus 3. You add these together. So minus 3 plus minus 3 gives you minus 6. Very good. 2, what did I say? D sine theta. That's my D. Sine, I'll write it over here, this arrow. There you go. Right, this is starting from here. This is not a 1. There. What am I doing? I don't know. 2 times 10 to the minus 6 sine theta equals m lambda. I'm going to write the words in now. Where is the m? What does it say? Angles which will observe the 2nd order maximum. So that will be 2 multiplied by the wavelength. 500, running out of space, times 10. I did not think this through. To the power of minus 9. I am so sorry. This is terrible. So this is my formula right here. Shift solve, I can calculate my angle. That's what I'm looking for. Or I can rearrange. Let's pretend I did not write that. Let's just look at this, yeah? Let's do that, shall we? We'll not talk about this. Yes, d sine theta m lambda. Rearrange for sine theta. I can just divide by d. Then you put the numbers in. And you can find the angle is 30 by doing sine minus 1. Sine minus 1 of 0.5. You will get 30 degrees. I butchered that. Okay, anyway. Let's move on. If the spacing between the lines on the grating increases, what happens to the angle? Well, of course, you just look at the formula. We want to see what would happen over here. I want to know if I increase this here, what happens to my angle. So I'll rearrange this just a little, just like we did above. Sine theta equals m lambda, and I'm going to divide that by d. Remember what I said? If it's below the division, it is inversely proportional. Increasing this will decrease my angle, and that's what they've mentioned here. It will decrease. I believe that's the end of the first topic. Yes, it is. So I'm going to stop this video here and continue on in the next one. Thank you.